Hello guys, it's time again for vacuum tube Tesla coils. You can see that the setup changed a bit from last time because I have a more traditional grid leak network now with two incandescent bulbs. And you might notice that the tube is a different one. I actually killed my old one because I also have two mods in series as a power supply now. And for the reason for that is I had two mods in parallel first, and I actually ramped up the feedback on this oscillator that it actually gave me 1 amp of anode current, which is also the cathode current, uh, of the tube at full variac. And it did actually give quite nice output. It gave me 30 centimeters of output, or closer to 35 actually. But the bad thing was that the tube didn't like that at all. It appeared to kind of like it at the start, but the problem is for tubes like these, the anode current only depends on the grid voltage, not so much on the anode voltage itself. Because you can see that this tube is a pentode, and there's a lot of wires in between of the cathode. The cathode goes up and down in this tube, which is supported by the springs, as you can see there. The cathode is actually there's so much metal between the cathode and the anode that the electric field between the cathode and the anode is not strong enough, it's not concentrated enough to rip sufficient electrons off. At 1 kilovolt, this tube only conducts 10 milliamps, which is close to no current at all, really. Well, compared to the current the tube is designed to take. The tube's maximum is about 0.6 amps. You can go about 0.7 amps without damaging the internals, but that's really pushing it. So that is the limit for the tube. So that's why people use microwave transformers in series. So they basically overvolt the tube instead of overcurrent the tube. But yeah, I guess I have spares now. Actually, these are GU-81 tubes. This is another GU-81M that I got from a friend. This one I got from Mutz or Curious Computer on YouTube, and this is from my friend Zick. Good people. Yeah, the broken one together with the original GU-81, the Iris 384, is actually over here. So I might need to show that later in some video. But yeah, it only depends on the grid voltage. So what this means is that if you overcurrent the tube, you also overbias the grid, because at 0.7 amps, the tube grids are basically already at their maximum. So going over only damages the grids. And the problem is when the grids melt, they like to sag into the cathode itself, so they short it out. Actually, the tube still works theoretically, but one part of the filament is actually bridged out by the grid having fallen into the cathode. So yeah, that's kind of sad. I do need to make a video because I actually have the video footage of where it happened. Anyway, it's still a Hartley oscillator, but I changed the topology. It's not grounded grid anymore, and I theoretically could have done this with grounded grid and just have a feedback, just have a grid leak to ground. The problem is with the grounded grid, the way I did it, the tube was actually part of the resonant circuit. The capacitance between the grids and the anode was part of the resonant circuit. And with the old oscillator, I discovered that the frequency shifts from 2 megahertz to roughly 3 megahertz. And I was wondering why that happens. Was it the secondary that was shifting, or was it the oscillator that was shifting? I discovered that it was, in fact, the oscillator that was shifting to higher frequency. Because at high power levels, the grid acts more of a resistor because it absorbs electrons because it's positively biased, right? So that means that essentially from becoming a capacitor, it becomes like a resistor. So it lowers the Q of the tank circuit so much that it acts more like a resistor than a capacitor. So it didn't act like a capacitor, so the capacitance of the whole system dropped, so the resonance frequency increased. And by doing the calculations, by removing the anode to grid capacitance from the 2 megahertz, I get calculated 3 megahertz, which is exactly what I'm also seeing. So it was that. So I switched topology where the grid is not part of the oscillator. And the good thing is it also reduces grid current, because the resonance current was also going from the primary coil to this tank capacitor to the grid that was also a tank capacitor. So the grid connections also needed to handle the RF current that is oscillating between, right? So over here is the schematic. You can see the things that I've changed. Basically, the thing that is changed is, first of all, the tank coil is the same, but this is connected to the ground. It's no, well, it's still kind of the same, but we see that this is no longer grounded, right? And the a tap is actually grounded, and the 2 extra turns is your feedback, and 2 turns is already enough. Theoretically, I can dial it up in another notch to get 0.5 amps, but I think 0.4, 0.45 is already enough for the tube. It gets about 2 kilowatts, but the output isn't exactly 2 kilowatts, so that must mean that it's still out of tune, and the measurements that I've done also confirm that. I actually built myself an RF amp meter for it. You can see we have the RF line here from the secondary, right? That goes over to ground. And there's a toroid. You can find these in old switching mode power supplies. They have them for the input filters and other stuff. And I bought some trash, and some of them, some chokes were in there. But this looks like to be from an output, maybe, or maybe part of a filter. I don't know. Anyway, there's a carbon resistor across it because it's a non-inductive type of resistor. And then we have a twist wire. It needs to be twisted to cancel out the inductance of the wire. And that goes into the meter. The meter is actually a standard voltmeter. And the thing is, this is still AC, right? So you need to rectify it to DC. So there's a bridge rectifier, and they made from Schottky diodes, a 10 nanofarad capacitor, and then of course a resistor to match the scale to the actual reading, because this was a 1 milliamp full scale meter. I actually reprinted the scale. That's a piece of paper, and I still have the old marking there. It was a 1 milliamp full scale meter. So you put a resistance in series that at 5 volts you get exactly 1 milliamp through the meter. But you also need to remember the voltage drop of the diodes, which is about 0.2 volts altogether from the bridge rectifier. And the resistance changes a bit, so at lower counts it's a bit less accurate, but you can do tests for that. Actually, it's around 2 amps indicated. And don't doubt my measurements, because I actually put a halogen bulb right there, and it did light up at it was around 2 amps of brightness, because I also tested with my DC power supply, and 2 amps was able to get the same brightness, so it has to be 2 amps. Tesla coils are low current. Yeah, right. What a nice myth that oftentimes gets spread around. Other big changes, the grid 3 connection. That is actually connected to the other grid 3 connection, which is there, and it is important to do so. I actually read some documents about this, because there have been some questions why tubes like the GU-81, well, the original, the RS384, why it has a top connection. It has a top connection, first of all, for modulation, because there's a way of grid 3 modulating these tubes. But the most important reason, from what I found in the documents, was to improve the shortwave performance of the tube. So at higher frequencies, of course, the inductance of the leads actually can act like a choke. So at higher frequencies, electrons will of course hit the third grid, and they actually develop a negative bias on it, because the choke is not able to remove that bias fast enough. So what they did is they put another shorter lead-out wire, so at higher frequencies you can also ground that and get the best performance out of the tube. So I'm not a ham radio guy, but I heard a lot of them complaining, but maybe that fixes the problems that they are having at higher frequencies with this tube. Yeah. Where was I? Yeah, I also added a choke here. well, self-explanatory, because there's still capacitance between here, and it could theoretically oscillate through these capacitors here. So this choke prevents that from happening, because if that were to happen, first of all, it stresses the connections more, and second, it's an added capacitance that we can't control, and we can theoretically have the same frequency shift happening that plagued the old oscillator. The secondary is still the same one. I don't have the dimensions there, but it resonates around 2 megahertz, and it's still out of tune. I know that because the meter at around 280 volts, it reaches the near maximum current, and over then it's not linear anymore. So that means that I'm maxing it out, and the extra power is basically being wasted into the tube and the tank circuit coil instead of going into the secondary. Also, important thing, I added a bunch more tape on the secondary because I once had an arc over happen. It wasn't a violent one at all, because I also have a protective spark gap system here. Problem is, the spark gap was after the incandescent bulbs, and one of them blew during that. So what I did is, this is the ground wire here, and I put another spark gap. There's actually a thin gap between those two nails. And if an arc were to happen, first of all, it would either go to this ground wire or it would go here, because over here it gets blocked with 2 doorknob capacitors in series. And I have heard stories from my friends that they had arc overs directly onto these capacitors and they lasted. So over here the current can travel, because it would also need to travel through this choke, which is also what it doesn't want to do. And you can tell by the choke construction here that it's basically isolated sections, right? That's kind of a fortunate accident, but it basically it isolates the high voltage sections between there, because the chokes still have inductance and they still have a resonance frequency, and over here you basically stop any resonance from happening, because if there was maybe resonance to happen, would happen across here in half of this coil, and this here would kind of act also kind of like a choke or something. It basically isolates the high voltage sections a bit from each other. And also, you can look inside the grid, you can see that there's no damage done. So it might red plate, but the tube is actually fine. And there's a fan cooling the top connections. You need to do that. Well, technically you don't need to do that, because I've seen people red plate these tubes all the time basically, but rather not risk it, specifically on the top connections. The bottom connections have enough thermal mass and isolation that they are fine. Look, they have a heat shield. It's fine. The power supply, it might benefit from extra capacitance, but this power supply is lethal. If you touch anything on this power supply while it's live, you instantly die. The power supply is also grounded, which might improve the risk of an arc over, but it also helps with the isolation of these microwave transformers, because they might arc over. I actually removed the secondary wire and I added the extra terminal there, which is a good change, I think. Yeah, it's not very well secured, but it's fine. I also removed the fan because the microwave transformers don't heat up much during operation. Alright, so enough talk. Let's actually power it up. Also, East German voltmeter there. And this is also an East German meter, you can tell by the mark. Okay. Well, I don't need the scope. Let's plug the tube in and watch it preheat. Nice. Also have, again, my filament control here. And the good thing is, if you size your transformer to the tube, you technically don't need a soft start. Technically. Because you can see it didn't light up that fast. It actually had a slower warm-up period because the transformer is limiting the current. Also, important thing, you can see the wires for the filament, the white wires there, are also, well, close to the anode lead. You can see there was an arc over there once because the wires were resting on each other. Well, this was resting on that. I was actually arcing the power supply directly to ground. Well, that's funny. Yeah, those capacitors are extra bypassing. There's another from the filament ends to the center tab. The GU-81 has that built in. It has two built-in 2 kilovolts, 800 picofarads of capacitance altogether, and it's also working as a grid 2 RF bypass. The GU-81 doesn't have that. And yeah, I found an old forum post which a friend of mine pointed me to. It actually mentions that someone did actually test the capacitance in them. The capacitance in them with high voltage, and the arc over happened around 2.2 to 2.5 kV. So these capacitors are 2 kilovolts for all that we are concerned about. So yeah, you need to clamp the voltage. What I will be doing is first of all doing another push pull with the GU-81 and using neon bulbs to clamp the voltage to 1 kilovolt. These clamp the voltage to around 1 kilovolt. 3 in parallel, only one string lights up at a time, but I expect to not get even 1 kilovolts into the grid drive, and if it does happen, there are 2 strings for backup. Yeah, I do talk a lot, don't I? Okay, let's turn on the fans. We check if the distance between the secondary and the primary pipe are in order. Yeah, that looks about fine, so we won't get any arc over. Famous last words. The variac is on 0. We turn the high voltage supply on. Look how quiet it is without that stupid fan. Okay, we turn it up. So, at around 60 volts roughly, maybe a bit lower because the scale is stupid. You can see the oscillator is, well, oscillating. The incandescent bulbs light up. The small light bulb there is barely lighting up because we don't have much voltage. We actually have 1 kilovolt of anode supply, and there's 50 milliamps of current totally being drawn by the circuit. And you can tell we have about 1 ampere of RF current through this coil. So this is my isolated arc stick, but because it's high frequency and isolated, you can't touch it with your finger, but you do get burnt. So you can see it's actually oscillating hard. And yeah, this definitely is 1 amp. If you doubt on my measurements. So let's actually turn the lights off, and let me turn my emergency light on. How nice. So let's see. Let's turn it up to 100 volts. Very nice, I think. 100 volts, around 140, 150. Grid 2 current. So we have, yeah, closer to 150 milliamps of current at 2 kilovolts. Let's ramp it up. Variac complains we're at 1.5 amperes. Tube is not warm. Around 2 amps. At 230 volts. The tube is glowing a bit, but that's the most we get. And I'm actually lowering the variac because you can tell that there's a lot of waste. Look, okay, I'm turning up the variac more, and there's not much move on the anode current, and the arc length doesn't increase either. So this must mean that the secondary frequency is much different than the primary frequency. So yeah, this needs another turn. I'm actually on the highest amount of turn ratio, and you actually need to isolate a bit of the turns. And I had, you can see that this primary is patched together from other stuff. But anyway, let me clamp my phone into the stupid fucking clamp. Anyway, I shouldn't be swearing, but you know. And let's enjoy. Let's enjoy the secondary arcing. Alright. 9 volts. Very nice. The tube isn't suffering much, is it? Alright, yeah, I need to optimize this further because you can tell by the tube red plating there's a lot of power being wasted. But the good thing is, the tube didn't die, and it's not dying. Trust me, I am paranoid. I'm checking the tube every time for damage, and it's not damaged at all. Yeah, it's drawing near 20 amp from the mains, so my 16 amp breaker doesn't like that at all. Well, it can tolerate it for a few seconds. I do want to get upgrade to maybe like 32 amps here, especially because surprised that I might be getting another more powerful tube and transformer on Friday, so I might release a video there. So yeah, thanks for watching. Please be careful with your vacuum tubes, and most importantly, high voltage. And always discharge your capacitors before they discharge into you. Well, thanks for watching, and bye.